Welcome. In this session, we'll explore stationarity of a function that has a vector argument. Let's begin by recalling scalar land. So let's recall that if we have a function that has a scalar argument and maps that to a real level, then a stationary point t, and we referred to that as t star, that has a first derivative at that point that's equal to 0. And we observed that that could be a minimizer, it could be a maximizer, it could be a saddle point. What we want to do is we want to redefine what a stationary point is. And what we'll do is we'll have an extension of this idea to a function that has a vector argument and produces a real level. And we'll say a stationary point. Now we'll write this as W star has, well, what we need to say is that the derivative at W star is 0. And the only way that we know from these sessions how to talk about a derivative is to talk about a directional derivative. So what we could say is in any non-zero direction, the directional derivative has to be 0. And that's what we mean by flat. We would write that mathematically as saying for any direction that we choose, as long as that was a non-zero direction, because otherwise the directional derivative limit doesn't work out very well, we want the derivative in direction v of the function evaluated at that point to be 0. And that is what we mean by a stationary point of a function that has a vector argument. So now what we can use the chain rule. So from the chain rule, and let's remind ourselves at this point that the chain rule is what's used in multivariate calculus to connect the gradient to the individual derivative components. So from the chain rule, what we had was that the directional derivative at any point is the gradient 1 form at that point times the vector direction. So what that implies in our case is that this implies that if the directional derivative is 0, then that implies that the gradient 1 form at that point has to be the 0, 1 form. So this is what we're doing, is we're defining a stationary point as one where in any non-zero direction the directional derivative is 0. And we're saying from the chain rule that means that can only happen provided that the gradient 1 form is always 0. And we can also write that, if we want to write that in component form, we can say that that the derivative of the function in direction j evaluated at that point that we're looking at has to be equal to 0. And these are if and only ifs that come out of the definition of the gradient 1 form. So let's recall further. So let's further recall that T star is a minimizer implies that T star is stationary, is a stationary point. And the converse was not true. So the result that we get when we go from scalar land into vector land is that if a point W star is a minimizer, that implies that W star is a stationary point. And we can go back to some of those earlier sessions and recognize that this idea of a global minimizer, a strict global minimizer, a minimizer, etc., all of those were defined with respect to vector arguments. So all of this applies directly. What we did was we defined it with vectors and then we restricted it to scalars. Now we're taking our understanding of scalars and we're bringing it back into vectors. So in both cases, for both, the converse is not true. So let's underline that not. That the converse is not true.